previous lecture, we were discussing where do a general descent optimization algorithm converge. We have found that a general descent algorithm almost always converges to a local minimum of the objective function. Now, slowly we will describe the methods, numerical optimization algorithms to find a local minimum of an unconstrained optimization problem. Before jumping to these optimization algorithms, in this lecture we will describe a very special analysis for optimization algorithms. In this lecture we will try to see if we go for a transformation of the variable, a transformation of the argument variable space, or if we apply a scaling of the objective function value, then how this transformation of the independent variables or the argument variables and the scaling of the objective function value affect the computation of gradient and Hessian for the objective function. We go for discussing this effect of the transformation of variables or scaling of variables and scaling of the objective function value on the gradient and Hessian, because we shall see majorly optimization algorithms, they do use this information of gradient and Hessian in computing the consecutive iterative points to reach at a local minimum point of the objective function. In fact, this analysis of the scaling of variable and scaling of the objective function values are important due to the fact that the objective function value or independent variables can vary substantially in magnitude is a crucial factor when solving many realistic optimization problems. For instance, suppose we have an optimization problem with the first independent variable, say x1, is in the range, say between 10 square to 3 times 10 square, and the second independent variable, say x2, is lying in the range of, say, 10 to the power minus 3 to 10 to the power minus 2. For example, you consider determining maximum speed of an aircraft or a jet engine and take the variable x1 as the displacement, and suppose this x1 is measured in the scale of meter. So x1 is lying in between 10 square to 3 times 10 square meter, and say this variable x2 represents the time in second. That is, here we are assuming that the x2 is lying in between 10 to the power minus 3 to 10 to the power minus 2 second, and you see that these widely varied range for x1 and x2 are physically possible. In this lecture, we look at how the gradient and Hessian, which essentially influence an optimization algorithm's speed, are affected by such a large range of scales. We notice that when this x1 is in this range and x2 is in this range, then if we go for calculating the norm value of the vector x that has components, say, x1 and x2, let's suppose we are going to calculate the Lebesgue norm, then we notice that in calculating this norm value, under root of x1 square plus x2 square, the effect of the value of x2 inside this calculation is virtually ignored. But in realistic problem, we cannot virtually ignore a particular variable's value just like that, because the example that I was giving, that you consider to determine the jet speed where x2 is in second, and a fraction of second has terrible influence in calculating the speed of a jet, and therefore we cannot just virtually ignore the value of the variable x2, even if it is ideally ignorable with respect to the value of x1. So what could be a possible remedy so that this x2 value, even if it is ignorable with respect to the values of x1, can have influence in calculation of norm of this quantity, norm of x? An obvious remedy to overcome such an issue is to apply a rescaling of the independent variables. For instance, let us suppose we are making a rescaling of the variables x1 and x2 by changing their units to x1 as in kilometer and x2 as in, say, centisecond. That means we are taking off a variable change, we are changing the variable x1 to say x1 hat by considering a rescaling that you consider x1 hat to be say 10 to the power minus 3 times x1, and you change the variable x2 to x2 hat, where x2 hat is given by say 10 square into x2. Then we see that the range of x1 hat and x2 hat are respectively, x1 hat is lying in between 1 by 10 to 3 by 10, and x2 hat is lying in between 1 by 10 to 1. Now in these rescaled variables x1 hat and x2 hat, we see that if we go for calculating the norm of x hat, where x hat has components x1 hat and x2 hat, in the calculation of norm x hat, we see that the values of x2 hat cannot be ignorable than that of the variable x1 hat. Here effectively what we have done, we have changed the variable space from x1, x2 to a new variable space given by x1 hat and x2 hat, where these x1 hat and x2 hat are given by a matrix multiplication, these 2 by 2 matrix times the vector x1, x2. Or in the vectorial form, let us write this x1 hat, x2 hat, this vector by simply the vector x hat, and let us denote this 2 by 2 matrix by say the matrix capital D, and we write this vector x1, x2 by the vector x. So what we have done here is that we have changed the variable space from the space of x to the space of x hat by this transformation, that x hat is equal to d times the vector x, where d is a diagonal matrix, or more generally we can simply consider x hat is equal to a matrix say capital T, a transformation matrix, times a vector x, where T we assume a non-singular matrix, and here in general let us suppose this x hat has n many components, and this x is then of n many components provided the transformation matrix is of order n by n. Now, well, we are making a transformation here that x hat is given by tx, and we are making this transformation so that in calculating this norm of x, no component of the variables x hat is ignorable with respect to other variable values. But what is the effect of this transformation in a general descent algorithm? We see that in a general descent algorithm, we broadly employ two particular steps. Those are identification of a descent direction at the current iterate xk, and then in the next step we go for identifying a step length to be taken along the direction dk. So any general descent algorithm is greatly influenced only by the calculation of the descent direction dk and the taken step length alpha k. Commonly for a continuously differentiable function, this descent direction dk is identified with the help of the negative gradient information. We usually consider the direction dk as simply the negative of the gradient of the function f at xk, or we consider to multiply a matrix bk with the negative of the gradient at xk, where this matrix bk is simply the inverse of the Hessian matrix, or we consider an approximation of the inverse of the Hessian matrix. This is about the choice of the descent direction dk in common general descent algorithms, and the step length alpha k is commonly chosen by one of the inexact line search methods, or you may employ any of the exact line search methods. And you know, if we go for employing exact line search or inexact line search, this alpha k is influenced by the calculation of the function values. For instance, if we go for employing, say, Armijo rule, or say the weak wolf rule, that gradient of fxk plus 1 transpose dk is greater than equals to c2 times grad fxk transpose dk. Here in the calculation of the step length alpha k, we notice that the value of the function f as well as the gradient of the function f greatly influence the calculation of alpha k. And therefore accumulating all, we notice that in the calculation of dk and alpha k in a general descent algorithm, the values of the gradient or the function value or the Hessian matrices are the three particular terms that greatly influence the calculation of this descent direction dk and this step length alpha k. And therefore, in finding the influence of a transformation of variable in a general descent algorithm, we have to find how this transformation of variable influence the calculation of the function value, of the gradient value, and of the Hessian matrix of the function. So we go for calculating the influence of the transformation of variables on the gradient, on the Hessian, and on the function one after another. Let us first calculate the influence of transformation of variable or scaling of variables on the gradient of a function. Let us suppose we are given a function of n variables which is given to be a continuously differentiable function, so that we can employ the chain rule in finding the partial derivatives with respect to the revised variables. And let for this function the generic argument variable is the vector notation x that has n many components, say x1, x2 till xn. Now on this variable vector x, we employ a transformation or scaling of variables by a matrix, say capital T, which is a non-singular matrix of order n by n. And suppose the matrix T transforms the variable x to the variable vector, say x hat, which is given by T times the vector x. Now in the new variable space, in the space of x hat, let us suppose the expression of the function f is changed to the expression, say f hat x hat. That is the function value at x, that is fx is equal to f hat x hat, and the expression of f hat in terms of f is given by, just you consider here to put x as this t inverse x hat. So we can write that this f hat x hat is simply f of t inverse x hat. Now we go for calculating what is the gradient of the function f hat with respect to the variable x hat. The expression of this gradient we wanted to compute in terms of the gradient of the function with respect to the variables x. So we wanted to find what is the relationship between this gradient of the function f hat with respect to x hat with the gradient of f with respect to the variable x. So we are trying to find an interrelationship between these two. So once this gradient is available to us, we can quickly calculate in the changed variable space what is the gradient of the revised function f hat. Now we see that the components of this gradient with respect to x hat are the partial derivatives of the function f hat with respect to the variables x I hat. So we first then try to identify interrelationship between this the calculation of partial derivative with respect to xi hat with the partial derivatives with respect to the original variables x1, x2 till xn. Towards this, we at first try to look at the relationship between x and x hat. We see that x and x hat are interrelated by x is equal to T inverse x hat. Now let's suppose this T inverse is a matrix, say capital A, which has components the ijth entry as Aij. By letting that T inverse is this matrix capital A, we see that we can write the components of x in terms of the components of x hat are given by x is equal to the column vector having components x1, x2 and so on till xn is equal to the matrix capital A times x hat. So explicitly you will have the first row as this expression, the second row as this expression, and the nth row is given by this expression. Therefore, explicitly, the function f hat in terms of the function f is given by f hat x hat is equal to f of the variable vector x which has components x1, x2 till xn. Now we consider to write the variables xis in terms of xi hats. So we get x1 is given by this first row. Similarly, you do write the second component x2 and end up with writing xn in terms of xi hats, which is given by this expression. Therefore, if we go for calculating the partial derivative of f hat with respect to xi hat, we get that del f hat del xi hat is equal to, by this equation with the help of chain rule, is given by del f del x1 into del x1 del xi hat plus del f del x2 times del x2 del xi hat plus so on till ending up with del f del xn times del xn del xi hat. This is for every I is equal to 1 to n. Now we see that this expression is equal to del f del x1 times del x1 del xi hat, which from this expression is given by simply the quantity a1i. The next term is similarly del f del x2 times a2i plus so on, ending up with del f del xn times ani, which in turn in the vectorial form is given by the row vector a1i as the first component, a2i the second component, ending up with ani the nth component, times the gradient vector of the function f with respect to the variable x, because the gradient of the function f with respect to x has components del f del x1, del f del x2, and del f del xn. And therefore this equation, on calculating partial derivatives of the function f hat with respect to x I hat, we have the gradient of the function f hat with respect to x hat is given by, which is given by, from this equation, that the first row as a11, a21 till an1 times the gradient of the function f with respect to x. The second row is given by a12, a22 till an2, and ending up with the nth row as a1n, a2n till ann, which we see that is given by this matrix, which is the transpose of the matrix capital A, and that is T inverse transpose times the gradient of the function f with respect to the variable x. So neatly we write the relationship between grad f with respect to x and grad f hat with respect to x hat by grad x hat f hat at the point x hat is given by the inverse of the transformation matrix, its transpose, times the gradient of f with respect to x at the point x. So this is the neat relationship between the relationship of grad fx and grad f hat. Now we shall go for calculating the Hessian of a function after scaling or transformation of variables. In calculating Hessian of a function, we consider a function f that is known to be twice continuously differentiable. Now, in calculating the Hessian of the function f with respect to the revised variable space x hat, we need to compute the Hessian with respect to x hat of the function f hat at the point x hat, which by definition is given by this vector, where the function f I hat at the point x hat is the partial derivative function of the function f hat with respect to the variable x I hat. So in computing the relationship between the Hessian of the function f in the space of x hat and in the space of x, we need to compute the relationship between the components in this Hessian matrix with the components in this Hessian matrix. That is, neatly we need to find what is the relationship between the ith row of the Hessian matrix with respect to x hat, that is the gradient with respect to x hat of the function f I hat, with the gradient of the function f I with respect to x, where this function f I is the partial derivative function of the function f with respect to the variable xi. So we are now going for identification of this relationship between the gradient of fi hat and gradient of fix. For finding this relationship, we look back to the relationship when the function f was changed to the function f hat we see that a scaling of variables gives us the relationship of the gradient with respect to the original variable and with respect to the revised variable is identified with this equation. Now we employ this equation to find the relationship between fix and its gradient with respect to x with the gradient of the function fi hat with respect to x hat. We just simply go for employing this relationship and we shall get that by this equation number 1, gradient x hat of the function fi hat with respect to x hat is equal to the inverse of the transformation matrix its transpose times gradient with respect to x of the function fi at x. This is for every I is equal to 1 to till n. Let us name this equation as say 2. Now we see that a relationship between fi hat and fi is given by these by the notation of fi hat, which by the chain rule gives us, which in turn gives us this function by definition is f1x. This by the definition or denotation we have f2x. This by the denotation is fnx. So we ultimately get this expression as f1x times a1i plus f2x into a2i plus so on till fnx times ani. Please sit with a pen and paper and then you cross verify. Otherwise, you will not be able to grasp the relationships and all these chain rules. Now, in this equation, you go for employing the gradient with respect to x hat. You will get that the gradient of f I hat with respect to x hat a1i grad x hat of the function fix plus a2i times grad with respect to x hat of the function f2x so on till ani times grad x hat of the function fnx, which by the equation 2 is given by T inverse transpose a1i times grad x f1x plus a2i grad x of f2x plus ani times grad x fnx. Now you put this equation 3 inside the definition of the Hessian of the function f hat with respect to x hat. Here you put the expression of all these components first, second and till the nth component. You will get that the Hessian of the function f hat with respect to x hat T inverse transpose the Hessian with respect to x of the function f at x times the inverse of the transformation matrix. You please cross verify this equation by plugging the expression in this equation 3 in the original definition of the Hessian of f hat with respect to x hat. So this is the need relationship between the interrelationship of Hessian in the space of x and Hessian in the space of x hat. Now so far we have been considering the effect of scaling of variables in the calculation of the gradient and Hessian of a function. Now next let me consider the effect of scaling of the objective function value in the calculation of the gradient and Hessian. That means let's suppose we are considering a scaling of the variable say y, which represents the variable for the function values fxs. That means we are considering to change this dependent variable y to some other variable say y hat, which is given by some constant multiplication, say some constant c, a real number, with the variable y. That means effectively we are considering to change the function value fx by a scaled function value c times fx. And now we wanted to calculate by changing f to cf how much the gradient and Hessian of the function f gets changed. Before looking into this scaling of the dependent variable or scaling of the objective function value, let me give you one example in identifying how important is the scaling of variables or change of variables before employing an optimization algorithm to identify a minimum point of a continuously differentiable function. To sense about this importance of scaling of variables, let me consider a numerical problem that you take, say, the expression of if a function of two variables x1 x2, which is given by some scalar lambda times x1 minus 1 square plus x2 divided by lambda minus 5 square of it. Here we are assuming that this scalar lambda is a non-zero quantity, and we consider this expression after applying a scaling of variables, say x1 hat x2 hat given by this 2 by 2 invertible matrix times the variables x1 x2. By this scaling of variables, the expression of the function f gets changed to f hat x1 hat x2 hat, which is given by x1 hat minus 1 square plus x2 hat minus 5 square of it. Now here I would like to request you to do a computer coding and check the following, that you consider minimizing this function f hat in the variable space of x1 hat x2 hat, and separately you consider minimizing the function f x1 x2. You consider these two problems, and in both the problems you go for employing the descent direction to be taken as the negative of the gradient of the function at the point xk hat, and take the step length alpha k to be chosen by exact line search. That is, alpha k is given by argument of the minimum value of the function f at the point xk hat plus alpha dk, or let's suppose dk hat. Here also we use the notation dk hat. Similarly, here in the space of x variable, you consider to employ the descent direction dk as negative of the gradient at xk and take alpha k as the exact step length, that is argument of the minimum of the function f at xk plus alpha dk. Or you may take the direction of descents by a unit vector along the directions of the negative gradient. So you consider here dividing this quantity by norm of the gradient at xk hat, and here also you divide this quantity by its norm. And for both the problems in the x hat space and x space, you take the stopping condition to be, say, norm of the gradient is less than 10 to the power minus 3, norm of the gradient here in the space of x space, the same quantity less than 10 to the power minus 3. Then you go for cross verifying that the number of iterations required for reaching at these stopping conditions starting from an initial point, say x naught is equal to minus 1 4, for different values of lambdas are as follows, that you take the lambda values as 2, 3, 4 and some more values I will write down. And here we take the column of number of iterations required in the variable space x space and the number of iterations required in the x hat space to reach at the stopping conditions are as follows, that for lambda is equal to 2, in the x space you shall require 13 number of iterations to reach at this stopping condition. But for in the x hat space, for any initial point, any point you take in the R2 plane, and then you go for employing this descent direction method, you will find that you are requiring only one iteration to reach at this stopping condition. For lambda equals to 3, you will find that in the x space, you will require 33 iterations, but in the x hat space, you require only one iteration. For lambda is equal to 4, you will require 29 iterations, but in x hat space you require just only one. For lambda is equal to 5, number of iterations required in the x space is 29, in x hat space 1. But if you choose lambda equals to 0.2, the condition is very terrible, that even after 2500 iterations, the method will not stop in the x space, but in the x hat space you will require just one iteration. Let me give some more values of lambda. For lambda equal to 0.25, you will require 34 in x space, 1 in the x hat space. For lambda equals to 33 and 0.5, the number of iterations required are respectively 5 and 9 in the x space, and in the x hat space you still need just only one iteration. So this table clearly indicates the effect of scaling of variables before you start employing an optimization algorithm to solve a minimization problem. Now I will end up by mentioning the effect of scaling of the dependent variable in calculating the gradient and the Hessian. Let us suppose we are considering a scaling of the function value by a constant factor, say c. Now to compute the gradient and Hessian of the function f, after the scaling of the function value, we need to compute the partial derivatives del xi and del 2 del xi del xj of c times fx. You notice that these both the calculations, the first order partial derivative and the second order partial derivatives, are simply getting multiplied with the factor c that we have factored in the objective function value fx, and therefore the gradient of the function f after this constant factor being multiplied is given by this constant factor c times grad with respect to x of the function f. And similarly for the Hessian calculation also, you will have this c times the Hessian matrix with respect to the variable x. So while calculating the descent direction of the scaled function, this CF, we need to take care about this constant factor, and while calculating the Hessian matrix of this scaled function CF, we need to take care about this constant factor. So just a quick look at the effect of this scaling of objective function value. We look at the stopping condition. Let's suppose we look at the condition that grad f at xk has norm say less than epsilon. So for the unscaled function f, if this is the stopping condition, with respect to the scaled function, the stopping condition would be gradient of f at xk has norm less than epsilon by c. Similarly, if we go for employing a stopping condition, as say the function values are not getting changed across the iterations, that means if you are considering the stopping condition as the difference of the function value in the consecutive iterate is not getting changed, then in the scaled function, this stopping condition will become if xk plus 1 minus if xk has absolute value less than epsilon by c. If however we look at the inequations for calculating the step length, let's suppose we are considering say the Armijo rule, then we see that in the scaled function f, these inequation do not have any effect, because in the scaled function this inequation gets revised to here c times f, here c times f, here is c times f. So all these c will get cancelled, and hence for calculating the step length with any of the inexact line searches, you can check that this scaling of the function has no effect. And eventually this scaling of the function value affects only at the stopping conditions. In the internal working of the step length calculation or the calculation of the descent direction dk, commonly there is no effect of scaling of the function value. With this comment, let me stop this lecture here. In the next lecture, we will go for identifying an effective stopping condition for a general descent algorithm. So far, we have been talking about the stopping condition as the gradient of fxk is less than epsilon. But the question is, does this condition gives an answer to the question that have we solved the problem which we wanted to solve? You notice that we aim for finding a minimum point of a function of several variables. And in finding a solution to this problem, we are ending up or we are stopping the algorithm once a point xk is generated so that this condition is fulfilled. Now here a question comes, is it an effective stopping condition for any given function f? That we would like to address in the next lecture. Thank you all for all of your kind attention.